So welcome everybody. Welcome to our Young Women for OR webinar. Just to let everybody know that this session is being recorded and we'll post it on our YouTube channel. So I'm just going to share my screen and I want to just explain one or two things if I can. There we go. So welcome. Here we are. Today's session is on routing and scheduling. My name is Paula Carroll. I am the chair of the Euro Wisdom Forum, and the Wisdom Forum is a Euro institution to support and encourage the participation of all genders in operations research. So we have a couple of objectives. So we want to advise the various Euro and OR institutions in Europe to be aware of issues facing women in OR. And today's session is towards our second objective about promoting young women at the early stages of their career in OR. And we have an overarching objective to promote a conversation about how OR can be utilised to help support a diverse and inclusive future. And Euro do have an EDI policy, so broader than just gender equality. So you can look at that on the Euro website. So today's activity is one of our initiatives, which is the Young Women for OR initiative. So we selected 12 young women at the early stages of their careers in OR, and each of them get a turn to present their research in a webinar like this. So today we have Mariana, Consuelo and Tu, and they are going to talk to us about their research work. But more than that, as well as our young women, we have a subject matter expert. So we are absolutely delighted to have Claudia here with us today. You can see that the screen is packed with all the wonderful things that she has done. So you can look at her website as well, her homepage, to see what she has done. And as well as all the things here that she's mentioned, I just want to call out that when we were setting ourselves up as the Wisdom Forum, Claudia was one of the VPs of Euro, and she gave us lots of advice on how we should go about setting ourselves up. So big thank you to Claudia for that, and thank you for being our subject matter expert today. So the format is each of our young women will speak. We won't stop at the end of their sessions for questions. They're each going to speak for 10 minutes. Then Claudia is going to comment a little bit on their presentations, and then hopefully we'll have some time for questions from the audience. So I will save that for later. I'm going to stop sharing, and Tu, it is over to you for your 10 minutes. So your screen's just coming up. There you go. Okay, over to you for the next 10 minutes, Tu.
Okay, thank you. Thank you, Paula. So my name is Tu. I'm based in the Lancaster University in UK, and my I specialize in optimizations, and my interest is mainly on the vehicle routing problems. So today I would like to give a talk about the project that I work with my colleagues, Adam and Burak. This is to find the fast upper and lower bound for the large-scale reward routing problems. So as you all of you have known, that transportation systems are very crucial in the modern world, and road transportation to give rise to an important family of the combinatory optimization problem known as vehicle routing problems. And this problem has received a lot of attention from many researchers due to the intensive applications. And our routing problem is a special kind of vehicle routing problems where the demands are located along the edges or arc rather than at the nodes. So here is how we model the road network on our routing problems. You can see there's two figures here. The figure on the left-hand side so use the real road network, and the figure on the right-hand side so use the graph representation of it. So normally I denote the graph as G's, okay, and we have the set of the vertex or the nodes. Each node will represent a key landmark or the road junctions or the place. The two-way road segment will be represented by an edges. We have the set of the edge E here. One-way road segment can be represented by an arc, and we have the set of the arc A. I denote L as the union set of E and A, and I call it as the set of the link. We have the subset of the required link that we need to provide the service. We call it as LR. We have the traveling cost for each link as well. So recently we encountered very challenging real-life routing problem given by our industrial partner, rootware companies. The problems contain multiple constraints and multiple objectives. And the instance itself is usually very large scale, contain more than 10,000 row segments in each instance. Moreover, the company wants like the fast algorithm that could produce the good upper and lower bound within just a couple of minutes for some reasons. These problems are in the context of the waste collection and can be modeled as the mixed capacitated routing problem with intermediate facility and a deadline. So besides the graph that I mentioned in the previous slide, we have the fleet of the vehicle with the capacity queue located at the depot. We have the demand for every required link, and we have the set of intermediate facility for this is the place where the vehicle can unload whenever they reach its capacity. We have the time limits that represent the maximum working hour of the drivers. One special characteristic of this problem is the number of the trip must be a multiple of a positive integer head. So now look at the following example. So in the UK, every household have the waste collection once every 2 weeks. And 1 week we have 5 working days. So the number of trips in this example must be a multiple of 10. Okay, and we have two objectives for these problems. The primary one is to minimize the number of the vehicles. And it is somehow equivalent to minimize the total cost of the problem because the cost caused by the vehicle usually dominate the other costs. If we only consider the primary objective, so we may produce a solution in which there exists a trip which is much longer than the other trips, which this may cause the unfairness between the worker. So now we address these issues by considering the secondary objective of the problem, which is to minimize the maximum trip duration. So here's the upper bound algorithm that we designed for this problem is based on the very famous Rufus and Cluster second heuristic. It contains two main phases. The first phase is to build the giant tour going through every required link. The second phase is the splitting phase where we need to split the giant tour into the feasible trips subject to the constraints of the problems. So in the giant tour phase, we will first construct the initial giant tour phase. We apply the fastest insertion heuristic, and this heuristic is designed for the vehicle routing problems, but we tailor it in order to work in our routing problems. We also make two other modifications. First, before we insert any required edges into the giant tours, we need to consider its orientations. The second here is we use the Euclidean distance instead of the true distance between any two nodes. This way can improve the running times of the algorithms. And however, this method has been proved work to be very well for the routing problem defined on the road network. And this papers this method is published in one of these papers. And after we got the initial giant tours, we will improve it. So we first apply the swap neighborhood. So the idea of this neighborhood is we consider to swap any two required link if it improves the total cost of the giant tours. And we still use the Euclidean distance in this neighborhood step. After that, we will compute the true distance between any two consecutive links. And this step can be done very quickly because we run the Dijkstra algorithm and we abort it whenever we reach the link that we want. And normally in practice, two consecutive links in the giant tours are quite close to each other. Okay, and the final step here is we apply the specification methods. And this method is the one we designed for the other routing problems and has been published in this paper. And we found that the extensions is rather complicated, but it's really worthwhile in reducing the total length of the giant tours. So the idea of this method is after we got the set of the edge in the giant tours, we can build the subgraph, right? And then we can delete some of the edges in this subgraph as long as it's still connected by computing the minimum spanning trees. And then we will rebuild the tour again by computing the minimum cost flow problems. Okay, so the order, so after this phase, we got the order of the required link travel along the giant tours, denoted as L1, L2, and until Lm. And here's the splitting phase. So first, we will greedily construct a set of the potential trips subject to the constraints of the problems. We denote len I as the number of the the maximum number of the required link can be serviced if the vehicle starts servicing the link Li. Okay, so if L1 equal to 10 here, so that means if the vehicle starts servicing the lane L1, it can be serviced at 10 required link at maximum. Okay, and then with the pool of the potential trips, so now we will contrast a solution that uses as few trips as possible with the backtracking step. So now I'm going to show you how this backtracking step work. So suppose that we have lane 1 equal to 10, lane 10 equal to 11, and lane 11 equal to 9. So without the backtracking step, if the first trip starts servicing the link L1, it can service 10 required link, right? And the second trip will start servicing from the link 11, can service 9 required link. So the total number of the required links serviced by those two trips is 19. Okay, so with the backtracking step, now if we only let the first trip servicing 9 required links, so from the link L1 to the link L10, L9, okay, and the second trips will start servicing the link L10, so can service 11 more required links. So the total number of the required link service in this solution is 20, which is obviously better than the previous solution. Okay, and the output of this phase is the number of the trips in the solutions, the upper bound, the number of the trips. But remember that the actual upper bound, the number of the trip must be a multiple of a positive integer head. So if it's, for example, if head equal to 10, and we got the solution with the 43 trips, so the actual upper bound of the number of trips must be 50. So all of the steps that we do before is only consider the primary objective of the problem. So now we consider the secondary objective of the problems. We will reduce the time limit 5 minutes X times, and we run the splitting phase to compute the solutions for the problem, satisfy the new modified constraints. Okay, we just repeat these two steps as long as the upper bound on the number of the trips is still the same. And I want to remind us we do not run the giant tour phase again. We only need to run the splitting phase. So this step can be done very quickly. I will skip the lower bound method because it may run out of the times, but the lower bound is based on the linear programming relaxation and the cutting plane. So now I'm going straight to the computational results. We are given some data sets from the company, but we cannot say any of them. So we try to create some artificial instance divided on the real-world network, and we try to do something to make that instance which is similar to the data set that we got. And here is the upper bound result. So this table shows you, the first two columns show you the information of the instance, so the name of the city and the number of the nodes. And the next two columns show you the number of the trips and the number of time visit to intermediate facility in the solutions. The next two columns show you the mean and the max trip durations, which is measured in hours. And here I set the time limit is 8 working hours per day. Okay, and the last column shows you the running time, which is measured in seconds. And look at the last column, you can see that it takes less than half a minute to solve all of the instances. And look at the columns, which is colored by red here. You can see that we already successfully addressed the secondary objective of the problem by reducing the maximum trip durations for every cases. And here is the lower bound result that we got. Again, look at the last column. It shows you the running time, which is measured in seconds. And it takes like less than 2 minutes to solve all of the instance. So our algorithm could produce the solution pretty quick, right? And look at the columns, ratio K column here. And you can see that this shows you the ratio between the upper bound and the lower bound in terms of the number of the trips. And we actually got the optimal solution in terms of the number of the trips for almost every cases, except for 2 cases in the New York City. And the next column shows you the ratio between the upper bound and the lower bound in terms of the total cost. And you can see that we all of the lower bound we got is over 90% of the upper bound for almost every case. So
1 minute now.
Okay, thanks. So in conclusion, the algorithm could produce the good upper and lower bounds for the problem within just a couple of minutes. And we have 3 future directions based on this project. The first is to decompose the problem into the number of the smaller problems. This way can help to improve the running times. And the second is to improve the local search heuristic. And this way can help to improve our upper bound results. The final is to design an exact algorithm for the single vehicle version of the problems. This way can help to police or to clean the individual chips in our solution to make the solution look more visually attractive. And here is the reference that I use in my talks. And thank you everyone for listening. And I'm happy to hear any suggestion or question if you have.
Thank you very much, too. That was really interesting. We're going to save all the questions till towards the end. Yeah. So thank you. And we are going to ask Mariana to share her screen and to go ahead. So Mariana has 10 minutes as well. We can see your screen. Yeah, if you want to put that. Perfect. Lovely. Off you go. 10 minutes.
Okay, thank you, Paula. Hello, my name is Mariana Oliveira. I'm a final year PhD student in engineering and management at Instituto Técnico in University of Lisbon. And I mostly work on operating room management and on surgical patient management. And today I'll present to you a solution to inform elective patient inter-hospital transfer that I've been developing together with my supervisors, Daniel Sanch and Ana Povo. So as
Mariana,
you may know,
put in slideshow because we are seeing your...
Oh, maybe I can check how to change that. I know that is a way.
Swap displays down.
Here, maybe.
No, in the 3 dots down.
But it is okay now?
Yeah, now that's okay.
Okay. This is because I have 2 monitors, so okay. But as I was saying, thank you, Professor. So as I was saying, as you may know, because of the aging of the worldwide population and the increasing demand for health services and the development of new and expensive technologies, there has been a higher challenge in managing healthcare, and along that, we have the higher pressure to reduce costs and maintain quality to the hospitals. And besides that, we need to manage conflicting interests, such as the staff, the patients, and even the hospitals and the systems interests. And particularly operating rooms are the center of costs and revenues of hospitals and represents the main point to entrance and exit in hospitals. So it is especially important to balance supply and demand for operating rooms. Even so, because if we don't balance it, we end up having high waiting times. And this, of course, have a direct implication on the health status of patients. So something that came up to our minds when we are thinking about this problem of balancing supply and demand is, what if in a certain point in time, hospitals have the capacity to receive elective surgical patients from different hospitals? Or what if we could ease patients' access to surgery in a nearby hospital? So what happens in Portugal is when the need for a surgery is identified, the patient is assigned a priority level, and related to this priority level, it is a maximum waiting time that they can wait. And so in this case, when we are building the model, we need to consider different needs for different patients. But what we observe in the Portuguese waiting list is that most patients fall into the normal priority level, so they have the longest waiting time target. But even so, we still have 40%, well, around 40% patients that actually wait past what is their waiting time target. So one solution that was implemented by the Portuguese government was something that they call the patient transfer notes or surgical voucher systems. So basically, when the maximum recommended waiting time is reached for the patient, they receive a surgical voucher that allows them to be treated in a different hospital. With this voucher, it comes also a list of hospitals that have the capacity to answer to the problem of the patient. And so now the problem is on patient side. So they need to first accept or refuse the transfer. If they accept, they need to contact the hospital that they chose, and they need to schedule all the surgeries and the procedures that are related with that. So what we see is that although we have a high number of issued transfer notes and surgical vouchers in Portugal, what we observe is that only around 18% of patients actually activated. Most of the patients just refuse to be transferred, but also a significant part of the patients let the transfer note expire. So the existence of this system actually suggests that it is in fact difficult to manage and balance supply and demand in Portugal. Then there is some literature on demand management amongst multiple hospitals, although it is quite scarce, but there are some related topics, such as network management, patient transferring management, distributed operating room planning and scheduling, and pandemic resource management. But well, of course, I will not get into that, but I just would like you to know that our work makes several contributions. First, it deals with proactive transfers instead of reactive transfers, which is a pressing problem in any health system that has to deal with this imbalance between supply and demand. Also, it is not limited to the pandemic setting, so we can apply the model to any system that has an imbalance between supply and demand. We try to solve it with a multi-objective optimization, and although, well, I think this is clearly a multi-objective problem, truth is that it is not a common method to use to solve it in the literature at the moment. It is also the first work that deals with the tactical problem, deals with this tactical problem, also considering distance. And this is an important thing because distance has a great impact on the experience of the patient. And also we consider several social objectives. So besides the distance, we also try to reduce the tardiness and the waiting time, as well as we try to minimize the reliability of transfers, which are, of course, objectives that are directly linked to the patient outcomes and satisfaction. So in this case, our objective is to develop a multi-objective model to optimize waiting list management and inform how hospitals could collaborate to clarify their pathways, the pathways for the patients, to reduce their overall costs, to reduce the tardiness and the waiting time for elective surgical patients, to improve the overall patient experience, to increase the fairness when we are scheduling, and to also increase the efficiency in operating room management. So the research question that we are trying to answer is, how can health systems take advantage of collaboration between hospitals and coordinate patient allocation? The decision that we want to make is which hospitals should establish guidelines for collaboration in order to tackle waiting lists, and the impact that we hope to have is on optimizing the network to achieve patient level and system level relevant objectives, while we still consider the individual hospital's missions. So for that, we propose a multi-objective integer linear programming model that first minimizes the waiting lists that are weighted by the waiting time category of the patients. So it minimizes the tardiness of the surgeries. Then we also minimize the transferring costs. And in this case, we consider different types of transfers. We consider transfers of collaborating hospitals, of non-collaborating hospitals. So we try to differentiate that. And besides that, we also try to minimize the transferring distance that each patient must undergo to have their surgery performed. In the model, we must also consider several constraints, such as the maximum distance between collaborating hospitals, to define the characteristics of the different types of transfers. Also, we need to consider, of course, the maximum capacity of hospitals to respond to the demand. And also we need to keep up with the evolution of the waiting lists, considering the transfers and the entries in the waiting lists. So our plan is to develop some computational experiments to first explore what happens when we try just to minimize the waiting times, which of course is the central objective for the patient. Then we are running an epsilon constraint algorithm to check the multi-objective results. Third, we want to compare our results with the real case of surgical voucher systems in Portugal. And finally, we want to develop some sensitivity analysis, particularly on waiting time targets, on the maximum distance that the patient can undergo to, and the costs of transfers. At the moment, we still do not have full information on the real Portuguese case study, but we were able to get public German data to construct some realistic instances. And running our model just with the objective of minimizing waiting times and allowing some transfers, we could actually confirm that those transfers could, in fact, have some impacts in the waiting list length. Of course, the impact that they have is different from specialty to specialty. For instance, in this case, we can observe that we have a higher impact on geriatrics. Here, for instance, we see that we have a higher impact for neurosurgery and not so relevant impact of transfers in ophthalmology. But what we observe also is that in any case, even for specialties that don't show any significant impact on the waiting list length, they actually have more balanced waiting lists throughout the waiting time categories for
1 minute, Mariana.
Okay, I'm just finished. For every specialty. So again, these are the same conclusions. We can balance waiting lists regarding waiting times. We are also currently working on the multi-objective results to generate some Pareto fronts to help managers to support decisions, but those are just very preliminary results because we are still trying to tune in the model and try to improve the efficiency of the model. So we are still trying to get Portuguese data, mostly some disaggregated data on the waiting list and on the capacity of hospitals to respond to surgeries and on the costs of vouchers. Also, we are still trying to improve our model, especially to deal with larger instances, because we have this limitation that we cannot deal with larger instances for the multi-objective. Also, we are also testing the single objective model coupled with a simulation model to see if we get some more realistic results. And of course, we still have a lot of work to do, but we believe that when we finished, we will be able to detect some important managerial insights for the transfer system, well, especially in Portugal. And this is a system that consumes a lot of public money and that is in fact poorly studied. So I hope you enjoy my presentation. This is the end of my talk. Thank you.
Thank you very much, Mariana. Another very interesting and very different topic. So we're going to go straight to Consuelo. Are you ready?
Yes, I'm ready.
Excellent. So if you share screen.
Can you see my presentation?
It's popping up now, yeah. Yes, okay. Perfect. Off you go. So you've got 10 minutes as well.
Okay. So first, good morning, everyone. My name is Consuelo Parreño. I am a mathematician, and my research background is on operational research. Currently, I am working as an assistant professor at the University of Valencia, Spain. And today I'm going to share with you our project, or the idea of our project, titled Optimizing Home Care Routine and Scheduling Problem, a mathematical model. This work is a collaboration with Miguel Reula and Ramón Álvarez Valdés from the University of Valencia, and with Francisco Parreño from the University of Castilla-La Mancha. All right, let's begin with the presentation. And I want to start with a map of the city where I work, of the city of Valencia. It is a lovely city in the east of Spain. On this map, I have marked the clinical university hospital with a square. And around the city, you see different points. These represent patients at their homes. Today, we are looking at how to assign and route the caregiver team to look after this patient. As you can see, I have drawn 3 routes from the hospital. Each route represents one member of the caregiver team. The topic of home health care routine and scheduling has received much attention recently, with several papers in the scientific literature discussing its complexities and peculiarities. One such paper is this one by Dimascolo in 2021. This paper emphasizes that the home healthcare routine and scheduling problem can be viewed as an extension of the vehicle routine problem. However, there are distinctive characteristics that lead to new constraints and objectives, setting it apart from the classical VRPs. So, the aim of the home healthcare routine and scheduling problem is to design routes for caregivers to care for a set of patients at home who require a specific skill. But we here focus on the home-based palliative care. But what's the difference? I mean, what's the difference between home-based palliative care from other home-based care? Here in this slide, you can see the definition provided by the World Health Organization. This definition underscores three key elements of palliative care. The first one is the multiple skills that caregiver team must provide. This means having a team of caregivers with varied skills to offer a holistic care. The second is the importance of the management of care continuity. This is crucial for maintaining trust and providing comprehensive care, especially during the transition from hospital to home and during the end-of-life phases of the patient. And finally, the weekly care planning. This allows care plans to be adapted to patient changes, needs, ensuring they receive consistent and personalized care. So let's go into the mathematical definition of the problem. We are looking at a set of patients shown in the figure as points, and a healthcare center, the green square. Caregivers start and end their route from the hospital, and visits need to be planned realistically. That is, considering distance, travel times, staff, and resource availability. Our model addresses individual and clusterized patients. The clusters are shaded in gray. Distance within a cluster are much less than distance between different clusters, so they can be considered constant. Patients might need several visits a week with a maximum of just one visit per day, requiring different caregiver skills. For instance, let's say the first patient March required 5 visits of skill 1, the second 3 visits of skill 2, and the last one requires 1 visit of skill 2. The first patient needs 5 visits, so he will be visited every weekday. But the second patient needs 3 visits. So should this be scheduled on Monday, Tuesday, and Friday, or other days? And the third one requires just 1 visit. Which days should it be? In our study, we associate each patient with a set of patterns defining the days in which the visit could be performed. The goal is to plan the visit over a 5-week week and assign them to the right caregivers. In the next table, we have so many parameters and sets we use in our work. I want to point out 2 things. First, we aim to have each patient seen by no more than 2 different caregivers in a week for consistency of the care. And second, caregivers have a maximum workload that cannot be exceeded. Okay, we develop a mathematical model together with a set of valid constraints to enact 8, but I won't get into the details of the model due to time, but I'd rather discuss the solution of, given by 5 different objective function in our formulation. When we talk about the challenge of home healthcare, we often want to minimize the total workload of the caregiver team. For instance, let us assume an instance having 50 patients and 5 caregivers. This figure shows the solution when minimizing the total workload time. Here, it can be seen that the total workload is around 57 hours, but there is a problem. The problem is work balance. One caregiver is overworked at nearly 88% of their capacity, but on the other hand, there are some caregivers who are not working at all during the week. Efficient routes, yes, but the workload isn't finally served. Let's now consider another objective function that maximizes the minimum workload percentage. The goal here is to balance the workload, and we can't balance workload percentage with this formulation. But there is a problem. The problem here is that we are leading to inefficient routes. In this solution, the increasing in the total workload is over 10 hours for the whole week. If we minimize the maximum workload percentage, we achieve a similar solution. The balance, we obtain a balance in the routes, but the total workload is longer than the total workload provided with the first formulation. So in this work, we try to mix it up using the total workload and maximizing the minimum workload percentage. If we do so, we can see that the total workload is just 1% higher than the starting point. And what about the balance? This method seems that the balance is also obtained, since the minimum workload percentage is 29 and the maximum workload percentage is 39. If we combine the total workload and the formulation minimizing the maximum workload percentage, we have a solution with a lower total workload, just 4 minutes shorter. But here, there are some caregivers that are not working during the week. So that's why we decided that the best objective for our formulation was the combination of the total workload and max-min objectives. Let's look at some results very, very quickly. We used the 26 instances by Capanera et al. In 2015. And in these instances, the number of patients ran from 40 to 162, and the number of caregivers from 4 to 11. In the first table, I only want you to see that we compare our model with the state-of-the-art mathematical model, and our model obtained more optimal solution and achieved a feasible solution for every instance test. If we compare the different objective functions with the same formulation, with our base formulation, we again see that if we only consider minimizing the total workload is shorter, but we don't obtain a balance in the workload. And if we use approach combining the total workload and the balance, we obtain a better solution. And finally, to assess the trade-off between the total workload and the minimum workload percentage, we use our best version with varying lambda values from 1 to 0. In figure, we have plotted average total workload against the minimum workload percentage. With lambda equal to 1, the work isn't balanced outward, and some caregivers don't have any work. But as lower lambda, we quickly start to see a more even balance of work, and the average minimum workload percentage goes up. For lambda values between 0.9 and 0.6, we get practical solutions that give decision makers flexibility. To conclude, we have developed a mathematical model. For the model, we have analyzed different objective functions. I conclude here, and there is still a lot of work to do, a lot of work to cover, to explore, and to refine. But I want to thank you all for your time and attention.
Thank you very much, Consuelo. That was really interesting. I have to say, I'm not being a great moderator this morning because I've been so engrossed in the presentations. I've been forgetting to ask people to stop, but I think they've done a wonderful job within the very short time frame of giving an overview of their work. Consuelo, can you stop sharing screen there?
Yeah.
And we will invite Claudia, who is our subject matter expert today, and maybe just to give us some thoughts or some feedback. They're very different presentations, so a hard job for you, Claudia.
Yeah. So, well, thanks, Paula. And well, I would like first to start thanking again Paula for inviting me and for the great initiative related to wisdom, for what we are doing, for what you are doing with that. And also I would like to thank the young OR speaker today for their very interesting presentation. Very different topics, but very interesting. Thanks for that. And so as moderator, I would like to give some, let's say, comments on each of the topic and the presentation that we have seen today. Eventually also some question. And I will go in the same order in which we saw the presentation. So starting first with Tu. So thanks for your presentation, very interesting topic. I liked a lot, let's say, kind of the practical flavor of what you presented today. I think it's definitely important. And I found, or at least the two features of the problem that you presented today that attracted the most my attention were related to, first, the close link that you have with road networks. I think, as far as I have seen, this is a really hot topic, because dealing with road network is definitely not easy. So you mentioned something related to how you deal with that in your presentation, but of course you just had 10 minutes. But I think this is definitely a hot topic. So I guess it would be ideal to stress how you deal with the fact that road networks have multiple features. Like, for example, you can deal with time or distance or speed or any other constraints that we might have in that. This was one first interesting feature. The second one was you were talking about the application that you mentioned, waste collection, and the novelty, at least to me, was one of the novelty was related to the presence of this intermediate facility. So if you can also give some flavor about how these intermediate facilities might help in getting better solution, more efficient solution, lower cost, and so on. What is the impact of having them? Was it something that was requested by the company you were collaborating with? So this was a curiosity that I had.
Go ahead. Yeah.
Oh, okay, thanks. Yeah, thanks for your suggestions. Yeah, that is interesting. Two ideas. And I think for the second one, this definitely is very helpful for to have the intermediate facility to lower the cost for the companies, because the vehicle can, whenever they reach the full capacity, they can unload the waste. And then they can come back to continue servicing some more work. And then just keep doing it several times during the days until it's reached to the time limit, and then they will go back to the depot in the end of the day. Yeah, that's interesting to see like how great it can improve the total cost. Yeah, I would think about this one, and maybe extend the research in this area.
Yeah, I think this is this has, of course, then other implications, like I guess that you were given the data related to, let's say, intermediate facilities with this kind of where vehicles can perform this kind of operations. But of course, another going on, you have the more tactical, let's say, decisions about when and where to locate these kind of facilities, which of course have an impact on the day-to-day operations then.
Yeah. So in the current research, I just try to do something like simple, like whenever the vehicle reach the capacity, so they need to go to intermediate facility. And before the end of the day, they also need to visit the intermediate facility to unload all of the waste before returning back to the depot. And yeah, I just trying to do like some greedily construct the solutions. Yeah, but I think it's quite interesting to investigate in this area.
Yeah, okay. And then just a final comment, but then I might eventually move to the other two talks, so that we eventually give some time also for the participant to ask questions eventually. Just a comment, because in the conclusion of your presentation, you mentioned that you wanted to either to improve the solutions that you obtained through your algorithm, or improve or make it more efficient. So I was wondering whether indeed for the kind of application that you are considering, you do need an extremely fast solution approach or not. So, because that is something I had the impression, like given even the application that you have, you might, I mean, you might, let's say, prioritize solution quality versus being fast. But also honestly, it seems that your algorithm is indeed already doing quite a good job when you compare with the lower bound. So yeah, this is quite interesting to see in which direction you can improve it. I mean, of course, now you have state-of-the-art algorithms, heuristic algorithms, also for the routing problems in general. So maybe you can take some ideas from there. Like, well, we know that now the state of the art is hybrid genetic search. So maybe you can have a look at this framework as well.
That's some wonderful ideas for two. So I think she has several directions now, and lots of really interesting ideas. And hopefully we might follow up some of these offline afterwards. But maybe we'll, Claudia, have a quick look at the other talks if you have some ideas or comments.
Yes. Yes. Oh, then going to Mariana's work, very interesting. Thanks. I really liked it. Well, from a global, let's say, the idea that came into my mind when listening to your presentation was the following. I think the what you presented is interesting, and what you have in mind that you specified during the talk and in the conclusion is coming up with sort of guidelines, right?
Yes, exactly.
To give to the hospitals as to potential ways to set up collaborations for this kind of program. And I think this is indeed a very interesting direction. And I was thinking about that you might, for example, use the model that you have developed in your work right here, and use it as let's say, as kind of tool in a simulator framework, that is simulating different kind of different setting or different instances, and then apply your tool to see what is the best to do, and coming up with decision trees or something like a decision trees, or very simple rules to give to the hospital. Well, if this is the setting, like if you are in the current situation in terms of capacity of the hospital, of demand, whatever it is, then you should do that. As I don't have that much experience working with the doctors in general, but the very limited experience that I have taught me that they do like very simple rules. Decision trees for them, it's ideal. So I guess this might be a very interesting potential continuation of your work, but I liked it really a lot. I was curious about many things, like what are the objectives and so on, but I think we don't have time to discuss about them. So so maybe that was my main comment on your work, and maybe using this as in a simulator to come up with these simple rules or decision trees.
Yes, thank you. That is a very interesting comment, because, well, again, also with my experience with doctors, what they want, well, they react better to simulation than optimization results. So it makes total sense to use a simulator with different scenarios. So yes, of course, this is a great suggestion. Thank you.
Oh, thanks to you. Thanks to you. Very interesting talk.
Thank you. Thank you. I'm glad.
Oh, and finally, I go to Consuelo. Thanks to you as well. Another, let's say, application related to health or healthcare in this case. Very interesting. I found there's, I had some, let's say, comments at the very beginning, but you answered all of them during the presentation. Many, they were mostly related to the fact that in this kind of application, you really have to care about, let's say, fairness with respect to caregivers. And this is what you pointed out, especially in the results, but also consistency. Consistency in terms of, and this is more on a patient perspective. So taking care about what is the best way to provide the care to the patients. And so this is typically dealt by looking at consistency of the plan. So my comment here would be maybe to emphasize a little bit more how you deal with consistency in terms of patient. As far as I understood, you deal with it by imposing a maximum number of caregivers that can visit the patients. I've seen other routine papers dealing with home care that treat consistency also in different ways, like having a schedule that is regular in terms of when do you visit, the time of the day, and so on, because this really has an impact on the well-being, let's say, of the patient. But again, very interesting work. So thanks to you as well. And sorry for being long, but I think we should give some time maybe to the audience to ask questions.
Thank you, Claudia, for those insights and feedback. And then there's, of course, opportunities to continue the discussions offline and in future venues when we're all collecting together. So I think Claudia, like me, had so much to digest there that it's so interesting. So again, well done to our 3 young women for OR. As Claudia said, we'll try and come to the participants for their questions or observations now. We won't have time to go through them all, but I'd like to take an opportunity to ask you to all turn on your cameras. And what we will do is try and take a screenshot or 2, and then I have some very important announcements to make, and then hopefully we'll just have a minute or 2 for questions. So again, I invite all of you to take a screenshot or 2, and you can share that on your social media. So again, we do aim to increase the visibility of our young women for OR and OR in general, just to show how collaborative a discipline it can be. I loved the range of applications today. So again, we have Dee, my colleague from UCD. I've lost you on the screen. There's too many people. Dee is going to help us out today because Nuncia is not here. So I would like just to make 2 quick announcements, and then we'll see have we time for questions. So I would like to share my screen one last time. So bear with me. So there we go. This was who we had today. So again, fantastic job. Well done. I thought our young women for OR did very well to try and pack such an amount into the short 10-minute slots. And a huge thank you to Claudia for taking time out from her very busy schedule, all the different things she's doing. I want to just announce a couple of things. So this is our current cohort of young women for OR. So there's now a fresh call for another group of women to apply. So we now have had 3 groups of women going through, and it's been hopefully for them a very valuable experience, and it's been a learning exercise for us. So the next call will open on the 15th of October. So let your network know that these opportunities are coming, and we'll have details on our LinkedIn page and our Euro webpage, so you can see the eligibility criteria there. So at most 3 years after your PhD or final year PhD students. So more information will follow. Couple of other things to let you know what's happening next. So our call is coming up for the next cohort. We do have one final webinar for the year, and Dolores is going to moderate that one for us. And our speakers will be Myrna, Mariam and Shishu. That will be coming up, details to be announced on our website. We'll also have a very nice event coming up in the winter where we're going to connect with the Informs Worms group and the UK OR Society WARAN group. They're both networks who support women in operations, research and management science. So that should be a very nice event. Again, details will be on our website. We, as well as our activities, we also have some research in progress. So we have bits and pieces that we're doing. We have a white paper that we've published, and we're working on some other pieces of research. So again, I won't pause now to tell you about them. And there you can see our contact details. And I want to say some thank yous. So huge thank you to Claudia, huge thank you to my Wisdom Committee, and also Nuncia, who is not here with us today. Her young daughter Sylvia is possibly the youngest woman in OR yet. She's only 2.5 days old, and I had the privilege of having a little cut with her yesterday evening. So I'm going to stop sharing there. We said we would stick to the hour, but we have maybe just 1 minute. If anybody has any quick question or observation, any burning issue that can't wait and be translated through an email or something. No. So we'll just give a little round of applause. So you can either do it in real time or your emoji or whichever you prefer to do. Well done to our young women. I thought they were excellent. And Claudia, thank you very much for your time. Our webinar today is recorded. It'll go up on our YouTube channel. And again, our young women, you can promote yourselves by posting our screenshots from today. So fantastic work. Well done. I don't think I mentioned in the list of things that's coming up is Euro 2024, when the young women will have another chance to present their work in a slightly less condensed fashion. They'll get all of maybe 20 minutes rather than 10. So again, well done to everybody. I'm going to stop recording now, and thank you all for your support, and look forward to seeing you at our future events.
Thank you, Paula, and thank you all.
Thank you.
Thank